right, so today we're diving into something that's a kind of a make or break topic when you're trying to land a senior software engineering role, especially during those technical interviews.
Yeah.
We're talking about how microservices communicate, which is,
Yeah.
pretty much the heart and soul of any distributed system.
It's the kind of thing that really separates the architects from the coders.
Exactly.
Yeah.
In a senior role, it's not enough to just be able to build a service. You need to understand how it fits into the bigger picture, how it interacts with all the other pieces.
Exactly.
Yeah.
And that's what interviewers are going to be looking for. Can you design a system that's resilient, that can scale, that can handle, real world complexity?
Right. And that all comes down to understanding how those services talk to each other.
Yeah.
Now, many of us come from, a background of building monolithic applications where everything's happening in the same process.
Right.
So it's easy to fall into the trap of thinking, oh, microservices are just like that, only spread out a bit.
Yeah.
But that's a dangerous oversimplification.
Yeah.
It's kind of like comparing a face-to-face conversation to a phone call with a really bad connection.
Exactly. It's a completely different beast.
And we need to understand why that is.
Yeah.
So let's start with performance. Because you mentioned earlier that it's just fundamentally different when services are chatting across a network versus just within the same application process.
Right.
Can you unpack that a little bit for us?
Yeah, absolutely. So when you're dealing with code that's all in the same process, everything's happening in memory, it's super fast.
Right.
And the compiler and the runtime can do all sorts of optimizations. They can even make some of those calls disappear entirely through a process called inlining.
Oh, wow.
Yeah.
I didn't even...
It's like magic, but none of that is possible when you have a network involved.
Right.
Right. Every single interaction between microservices means, you're packaging up data, you're sending it across the wire, and then the other service has to receive it, unpack it, and send a response back.
Right. Right. It's like sending a letter versus just handing a note to someone sitting next to you.
Exactly.
And that round trip, even if it's just within the same data center, that takes time.
Yeah.
It introduces latency.
It does. And we're not talking about nanoseconds here. We're talking milliseconds, which may not seem like much, but it adds up fast.
Yeah, yeah. It's almost like every conversation has this built-in pause.
Yeah.
It's like a delay on the line.
Exactly. And that latency can really change how you think about designing your APIs.
Oh, interesting.
An API that works great within a monolith with lots of small, frequent calls.
Right.
That can become a huge bottleneck when you're dealing with microservices.
Oh, I see.
Right. Because suddenly all those back and forth trips across the network, those really start to add up.
Oh, yeah. So you have to think differently about how you're structuring those interactions.
Yeah. You have to be more mindful of how chatty those services are being.
That's a good way to put it.
It's like the difference between having a quick chat with your colleague and writing them a formal memo every time you need something.
Okay, I see.
And then there's the data itself.
Right.
Within a single application, you're often just passing references around, pointers to the same data in memory.
Right.
But with microservices, every time you send data over the network, you have to serialize it, which means converting it into a format that can be transmitted. And then on the other end, you have to deserialize it.
Right, right.
And both of those steps take time and resources.
So suddenly something that was almost an afterthought in a monolith, the size of the data you're passing around, that becomes a really big deal.
It does. You can't ignore it.
You can't just send, massive objects back and forth without thinking about the consequences.
Right, right.
Because it impacts your network bandwidth, your latency, the amount of processing power you're using on both ends.
Right. And it might even lead you towards, different strategies for handling that data, like maybe only sending the absolutely essential information or aggregating data on the server side to reduce the number of calls you're making.
Exactly. Or maybe even offloading large binary data like images or videos to a separate storage service and just passing around URLs or references.
Right, right. It's almost like you have to think about data transfer as this precious resource that you need to use sparingly.
Yeah. It's like you're paying for every byte you send.
Okay, I see.
And then, of course, there's the choice of serialization format itself.
Oh, right.
Something like JSON, which is very human readable.
Right.
That's not always the most efficient option, especially when you're dealing with a lot of data.
Right, right. So maybe something like protocol buffers? Right.
Or flat buffers.
Exactly.
Which are more compact and faster to process.
Yeah. They're more machine friendly.
Right, right.
The bottom line is that you have to be aware of the fact that you're working with a network.
Right.
You can't pretend that it's just all happening locally.
You can't abstract it away entirely.
Yeah.
Yeah. Okay, that's really helpful. And speaking of things you can't just ignore, let's talk about managing interface changes.
Yeah.
Because in a monolith, if you need to tweak an interface, it's often a pretty straightforward process.
Yeah, you change a function signature, your IDE helps you update all the references.
Right.
You deploy the new code, done.
Right, right.
Yeah.
It's all very self-contained.
Yeah.
But with microservices, it's a whole different ballgame. Because now you have all these independent services that might be deployed and updated at different times by different teams.
Exactly. And if you make a breaking change to an interface, if you rename a field or remove an endpoint, you can't just deploy that change and expect everything to keep working.
Right.
Right. You either have to do a big bang deployment where you update all the affected services at the same time, which is a logistical nightmare, especially if you have a lot of teams involved.
Oh yeah, trying to coordinate all that would be a huge headache.
Yeah. Or you have to adopt a more gradual approach, a phased rollout.
Right.
Which can be more complex, but it gives you more flexibility and control.
Can you give us some examples of what that might look like in practice?
Sure. So one common approach is to maintain backward compatibility for a while.
Okay.
You introduce a new version of your API, but you keep the old one running as well so that services that haven't been updated yet can still communicate.
Okay, so it's like having both versions of the API available for a certain period of time.
Exactly. And you might do that by using different URL paths or headers to distinguish between the versions.
Okay, I see.
Another technique is to use feature flags.
Right.
Which allows you to selectively enable new functionality for certain users or services.
Okay, so you can kind of roll things out gradually and test the waters as you go.
Exactly.
Right.
The key is to decouple the deployment of the interface change from the update of the consumers.
Okay, I see. So it's all about reducing the risk and the potential for disruption.
Yeah. It's about embracing the fact that you're working in a distributed system where things can't always move in lockstep.
Right. Right. And that brings us to another area that can be, well, let's just say it can be pretty hairy in distributed systems, error handling.
Yeah.
Because, within a single process, when something goes wrong, the possibilities are somewhat limited.
Right. You have your exceptions, null pointer exceptions, index out of bounds.
Right. It's all fairly predictable.
Yeah. And then you have those more catastrophic failures that might bring the whole application down, but generally things are pretty deterministic.
Right. Right. You know what went wrong and why. But the moment you introduce a network into the equation,
right,
suddenly you have this whole new universe of potential failures.
Yeah. It's like opening Pandora's box.
Because now you're relying on infrastructure that you don't control.
Yeah. Networks can go down.
Right.
Downstream services can become overloaded and unresponsive.
Right.
Connections can be dropped.
And there's a helpful way to think about these different types of failures, right?
Yeah, there's a model that categorizes network failures into 5 main types.
Okay.
The first one is crash failure.
Crash failure.
Yeah, that's when a service just completely stops working and needs to be restarted.
Okay.
Then you have omission failure.
Omission failure.
Yeah, and that's when, a request or response gets lost in the ether, or a service just stops sending the updates that other services are expecting.
So it's like a crucial piece of information just disappears into the void.
Exactly.
Okay.
The third type is timing failure.
Timing failure.
That's when messages arrive either way too late or, in some cases, even too early.
Okay.
The fourth type is response failure.
Response failure.
That's when a service does respond, but the response is either wrong or incomplete.
Okay, so it's like getting the wrong answer or only part of the answer.
Yeah, exactly.
Okay.
And then finally, we have arbitrary failure, sometimes called Byzantine failure.
Okay.
And this is the really tricky one because it's when a service is behaving erratically, maybe producing incorrect or contradictory results.
Right.
And different parts of the system might have different views on whether a failure has even occurred.
So it's like trying to debug a ghost in the machine.
Yeah, pretty much.
Okay, so we've got this whole spectrum of potential failures.
Yeah.
And what makes it even more challenging is that some of these errors are transient.
Yeah.
It might just be, temporary glitches that resolve themselves quickly.
Exactly.
Whereas others are more serious and might require manual intervention.
Yeah.
So how do we even begin to deal with all of this?
Well, first of all, you need to accept that failures are inevitable in a distributed system.
Okay.
You can't prevent them entirely, but you can design your system to be resilient to them.
Right. So it's all about graceful degradation.
Exactly.
And part of that is having robust retry mechanisms.
Yeah. If an error is likely to be transient, a dropped network packet or something, then retrying the operation after a short delay might be all you need.
Right.
But you also need to be careful not to overload the system with retries.
Right. So having a good back-off strategy is important.
Yeah, you don't want to create a retry storm.
Okay. Okay. And then there's the issue of error semantics, right?
Yeah, that's crucial. You need to provide enough information about the nature of the error so that the client service can make an informed decision about what to do.
Right, right. So it's not just about knowing that something went wrong, it's about understanding why.
Exactly.
And a good example of that is HTTP status codes.
Yeah, the 400 series codes, those tell you that there's a problem with the client's request.
Right.
So retrying the same request is probably not going to help.
Okay, whereas the 500 series codes indicate a problem on the server side.
Right.
And some of those, like 503 service unavailable, might be temporary, suggesting that a retry after a delay could work.
Yeah.
Right.
Yeah.
Right. But the point is, regardless of the protocol you're using, whether it's REST, gRPC, message queues, whatever, having well-defined error handling mechanisms that provide context is absolutely essential for building resilient systems.
Absolutely. It's what allows clients to recover gracefully from errors and prevent those failures from cascading through the system.
Right, right. And it's also something that interviewers are going to be paying close attention to when they're evaluating senior candidates.
Yeah.
Because it shows that you understand the complexities of working in a distributed environment.
Exactly. It's not just about writing code. It's about designing systems that can handle the real world.
Okay, so we've talked about performance. We've talked about managing interface changes.
Right.
We've talked about error handling.
Yeah.
Let's shift gears a bit and talk about the technologies that are available for microservices to communicate.
Sure.
Because it can feel like a bit of a jungle out there.
It can. There's a huge variety of options.
Right.
You've got REST, gRPC, message queues, service meshes.
Right. And it's easy to get caught up in the hype and just gravitate towards the latest shiny new thing.
It is.
But the reality is that choosing a technology should be driven by the specific needs of your system.
Yeah.
What are the communication patterns that you need to support?
Yeah.
What are your reliability requirements?
Right.
What are the skills and experience of your team?
Right. All of those things matter.
Right. And you mentioned earlier that choosing a technology often comes with adopting its inherent assumptions and limitations.
It does.
Can you give us an example of that?
Yeah, sure. So let's say you have a system that's based on simple request-response interactions.
Okay.
A client sends a request, a server processes it, and sends back a response.
Right.
And you decide to use a message queuing system like Kafka for this.
Okay.
Now, Kafka is a fantastic technology,
Right.
but it's really designed for asynchronous communication and high-throughput event streams.
Right.
So if you're just using it for simple request response,
Right.
you're adding a lot of complexity without really getting any benefits.
Oh, okay.
Right. It's like using a sledgehammer to crack a nut.
Right, right. Or using a Formula One race car to commute to work.
Exactly.
Okay, I see.
On the other hand, if you have a system that's inherently asynchronous,
Right.
where you need to process events in real time,
Right.
then Kafka might be the perfect choice.
Okay, so it's all about matching the technology to the problem.
Yeah.
Right.
You need to understand the trade-offs involved in each technology and make a conscious decision based on your specific needs.
Right, right. And that's something that you should be prepared to discuss in a technical interview.
Yeah. Interviewers want to see that you can think critically about technology choices.
Okay, so to sum things up,
Yeah.
communication between microservices is a complex topic.
It is.
Right.
It's not something that you can just learn overnight.
Right. And it's something that you need to have a deep understanding of if you're aiming for a senior engineering role.
Exactly. It's one of the things that separates the senior engineers from the junior engineers.
Right.
You need to understand the performance implications. You need to understand how to manage interface changes. You need to understand how to handle errors.
And you need to be able to articulate all of that clearly and concisely in an interview setting.
Yeah.
So for those of you who are preparing for technical interviews, my advice would be to really dive deep into this topic.
Yeah.
Read articles, watch videos, practice explaining these concepts to others.
Sure.
And don't be afraid to ask questions.
Yeah.
Because the more you understand about how microservices communicate, the better prepared you'll be for those tough interview questions.
Exactly. And the better engineer you'll be.
Absolutely. Well, thank you so much for joining us for this deep dive.
You're welcome. It was a pleasure being here.
And for all of you listening out there, keep learning, keep practicing, and good luck with those interviews.
Good luck.
Okay, that's all for today.
Bye.